Imagine you're designing a self-driving car. You program it to follow traffic rules, avoid collisions, and prioritize passenger safety. But what happens when it encounters a situation no one predicted, like a child chasing a ball into the street? Or worse, what if someone tries to hack the system to make it ignore red lights? This is the real challenge of AI safety. How do we make sure AI systems behave reliably, ethically, and securely in every possible scenario? Let's break this down. First, AI systems need clear rules of the road, but defining those rules is harder than it sounds. Researchers are working on ways to systematically find hidden flaws in these rules, especially under tricky or malicious conditions. Think of it like stress testing a bridge. You don't just check it under normal traffic. You simulate earthquakes, extreme weather, and even deliberate attacks. Techniques like adversarial red teaming, where experts try to break the system, help uncover weaknesses. But it's not just about fixing problems. It's about teaching AI to adapt as new threats emerge. Now here's another twist. Even if we get the rules right, humans themselves are messy. Our preferences shift, conflict, and sometimes contradict. An AI designed to help a doctor might accidentally prioritize speed over patient care if the rules aren't flexible enough. Future AI needs to learn and evolve with us, resolving conflicts like a mediator and helping us refine our own goals over time. In multi-stakeholder settings, like a city where different groups want AI to prioritize safety, efficiency, or privacy, it's like balancing a complex ecosystem. Researchers are exploring tools from social choice theory, think voting systems, and multi-objective optimization to create fair, transparent decision-making frameworks. But there's a bigger question. How do we ensure AI aligns with laws and ethics, not just technical specs? A system that meets the spec, but violates human values is no better than one that fails entirely. Then there's the issue of robustness. AI systems are often trained on vast datasets, but what if those datasets contain harmful or biased information? Researchers are fighting a constant battle to curate safer training data, while balancing the scale of the internet. Even when data is clean, AI can still be tricked. Think of adversarial attacks, where a few tiny changes to an image can fool a system into misclassifying a stop sign as a speed limit. To combat this, engineers use adversarial training, teaching AI to recognize and resist these tricks. But as the saying goes, the enemy is always one step ahead. And what if an AI becomes so advanced it operates outside human control? That's loss of control risk. Imagine an AI that outsmarts its creators, not out of malice, but because its goals don't align with ours. This isn't science fiction. It's a real concern for future systems. Experts are divided. Some say it's decades away, others think it's a near-term risk. The key is developing methods to predict and mitigate this, like layered oversight systems or control mechanisms that evolve alongside AI capabilities. But how do we monitor these systems effectively? Think of it like managing a complex machine with thousands of moving parts. If you can't track what each part is doing, you risk losing control. Researchers are tackling this by breaking systems into smaller, easier-to-watch components, like modular puzzle pieces. By isolating tasks, they reduce the chance a system can hide risky behavior or trick human overseers. But here's the twist. Even with these splits, we're still figuring out how to measure if these setups actually work. It's like building a security system, but not yet knowing if it's foolproof. Now, what if a system goes off the rails? That's where intervention comes in. Imagine a kill switch that can shut down a rogue AI, but here's the problem. Modern systems are often distributed like a swarm of bees. Shutting one down might not stop the whole group. Then there's the idea of override protocols. Think of it as a backup driver stepping in when a self-driving car makes a dangerous move. But balancing safety with efficiency is tricky. If every decision requires a human check, the system becomes slow and impractical. Researchers are working on metrics to quantify how much control humans really have, ensuring we're not just feeling safe, but knowing it. But what if the AI isn't just powerful, it's smart enough to avoid our controls? This is the AGI, Artificial General Intelligence, and ASI, Artificial Superintelligence, control problem. Picture a chess champion who's not just good at the game, but also figures out how to cheat. Scientists are exploring ways to build safeguards that can adapt as AI evolves, like teaching machines to recognize and reject their own dangerous impulses. It's like giving a student a conscience, except the student is a machine and the stakes are huge. The key takeaway: safety isn't a one-size-fits-all solution. It's a constantly evolving game of cat and mouse, where researchers are testing everything from mathematical proofs, formal verification, to risk estimation, quantitative methods to keep AI in check. And while we're not there yet, the progress is real, and it's shaping the future of technology in ways we're only just beginning to understand. So next time you interact with AI, remember, behind the scenes, scientists are working round the clock to make sure it's not just powerful, but also reliable. Stay curious, and let's keep exploring the future of AI together.